Okay, problem 5.100 says a 100-foot wide river with a flow rate of 2,400 feet cubed per second flows over a rock pile as shown in the figure. Determine the direction of the flow and the head loss associated with the flow across the rock pile. Okay, so as the flow goes over this rock pile, there's going to be a bunch of non-isentropic happenings like separations and etc. So we're going to develop a head loss as it goes across those rocks. So let's first jot down all of our givens for this problem. Okay, we're told that there's a width in this river, and that is 100 feet. And we're told that there's a flow rate, Q, which is 2,400 feet cubed per second. Okay? So the heights were also given. At section 2, the height at the top of the surface, Z2, is going to equal 2 feet. And at section 1, we have 4 feet. Okay? So let's start by jotting down our conservation of energy equation. And that just says over our, let's draw some stream tube that goes between 1 and 2. Right, so this is like our control volume. Okay? That energy change looks like this. We have the energy at 2 from pressure, so P2 over gamma plus V2 squared over 2G plus Z2 has to equal P1 over gamma plus V1 squared over 2G plus Z1 plus the shaft work head minus the head loss. Okay? So there's no shafts, pumps, or anything, turbines in this problem. So we have no shaft head, so that disappears. We also know that location 1 and location 2 are the top of a free surface, so their static pressures are just atmospheric. So they're going to cancel each other. So these two terms disappear. And that's it. So now we could rearrange this problem, and we will be able, we'll just have V2 squared right over 2G plus Z2 has to equal V1 squared over 2G plus Z1 minus the head loss. Alright, so now we need to determine some values. So we need to get what the velocities are. Right? So how do we get this? So to get velocities, let's use continuity. Okay, so continuity says that Q is equal to V1 times A1, which is equal to V2 times A2. Okay. So the area, we'll notice, is twice the other one because we have 2 foot by 100, and then the other side we have 4 foot by 100. It's going to be the total area. So we can then say that V2 is just going to equal 2 times V1. Okay. V1 is going to equal Q divided by A1, and therefore we're going to have 2,400 divided by A1 is 4 times 100, and that is going to equal 6 feet per second, and therefore V2 is going to equal 2 times that, 12 feet per second. Okay, so now we have V1 and V2. We have Z1 and Z2. Therefore, we can solve for our head loss. So let's go and plug in some values. Okay, so that was V2 squared, which is 12 squared, divided by 2 times G, 32.2, plus Z2, which was 2. That has to equal V1 squared, 6 squared, divided by 2 times G, plus Z1, which was 4 feet, minus the head loss. Okay, one equation, one unknown. I get that the head loss is equal to 6 squared minus 12 squared over 2 times 32.2 plus 2, and that is equal to 0.3229 feet. Okay? So that's what our head loss is, and the problem asks us whether or not or which direction the flow is going. Okay? So because my head loss must be positive, must be a positive value, otherwise we would be going against the second law of thermodynamics. Okay, so our head loss is always positive, and since we did get a positive value, that means we know that our initial guess was right. That means we are going from 1 to 2, and therefore the flow is going from right to the left.